Hello, everyone, and welcome back. Today, we're going to switch gears a little bit and we're going to talk about something a little bit different. They are called limits, and we'll talk more about those in a second. But essentially, the reason why we're going to talk about them is because the big problem that we realized in our last lesson was that when we have this function for instantaneous rate of change, f of a plus h minus f of a over h, where we have this interval h that we're trying to make as small as we can, preferably zero, and it gives us this big problem where we have to divide by zero. And essentially, the reason why we're going to look at limits is because they give us a handy way of trying to look at a specific point that maybe isn't necessarily defined, and we can use that to help us gather a bit more information. And the way I'm describing this, I'm sure it sounds a little bit cryptic right now, but just hang in there. We're gonna use this. We're gonna practice this concept of limits for a few lessons, and by about 4.6, we'll put it all back together, and hopefully, it'll make a bit more sense as to what's going on. I'll leave a lot of this for you guys to read over on your own, but I'm gonna give you guys the quick bullet points introduction. So essentially, we have this thing. It's called a limit, and when we read it as the limit of f of x as x approaches a of f of x. So going through this piece by piece, it is the limit as x approaches a of f of x equals L. And basically what that means, we're just basically looking around the function and seeing what's going on. So we're not necessarily looking at the specific point on the function. If we were just looking at a point f of a on our function, we would just be looking at that specific point. But instead of looking at the point specifically, what limits allow us to do is to look around the function, what's going on to the left of it and to the right of it, to give us a bit more information. So even if we don't have a specific point there, it can help us out. And just to help this make a bit more sense, let's talk a bit more about these. So in addition to general limits, we can have what's called a left-handed limit or a right-handed limit. So a left-handed limit, which we mark like this, and you're going to notice this little superscript minus sign next to it, next to the A. Basically, what we're doing is we're looking at, let's take that parabola example again. And what this means is we're looking at, from the left, where's our curve headed? So what is the y value that we're approaching on this side? We can also have a right-handed limit, which we mark with a little superscript plus sign. And what that's asking us is, if we look at the curve from the right, where are we approaching? In this case, it's the same spot, but not always. We could have another parabola that looks like this, but we could have it discontinuous at this point, and then maybe go into a line here, maybe more of a piecewise function. So in this case, the left and the right-hand limits are approaching two very different things. So essentially, what those are marking is, from the left, what y value are we approaching for our points? And again, at this point, we notice that there's two different points here. There's only one that's the actual point for the function. So that's f of a here because it's the filled in one. We have this hole here just to mark that's the beginning point, but it's not our actual y value, our function value. But if we're looking at from the right-handed limit, then that's what we're looking at. If the limit as x approaches a from the right of our function f of x. And then, of course, the other side is going to be the limit as x approaches a from the left of f of x. Sorry, I can't remember if the last one I said right or left, so just keep those straight. Now, just one more quick thing I want to warn you guys about, because I always have a few people that struggle with this one. Just be careful here. Sometimes we're going to have approaching negative numbers. We could have approaching -5 from the left. So just be careful. Make sure you know which one's which. If it's a little superscript minus sign or negative sign, then it's then we're just talking about the left-hand limit. If it's a negative sign next to the number, then we know that we're talking about a negative x value for our point. So just make sure you keep those two straight. Let's talk about the criteria for a limit. So sometimes we want to know if there is a limit that exists. And the way we do that is by comparing the left-handed limit and the right-handed limit. Let's start by taking a look at a limit that exists. Let's say this point here. Now the reason we know this exists, let's take a look at our criteria. The first thing we need to know is, does the left-hand limit exist? So in this case, we're looking from the left, it does approach a point. So in this case, it exists. So condition 1 is satisfied. Condition 2, let's take a look. It says the limit as x approaches a from the right exists. So in this case, we're approaching a point, so that one exists. And lastly, the limit as x approaches a from the left is equal to the limit as x approaches a from the right, which essentially means, do they approach the exact same point? In this case, they do, so that exists. Let's take a look at some examples of ones that don't exist. Let's say we could have something like, let's take that piecewise function that we dealt with in the last problem. So in this case, let's take a look from the left. It approaches a point, so the limit as x approaches a from the left exists. Let's take a look at condition 2. And now it's talking about the right-handed limit. And yes, again, we're approaching a point, which is going to be the hole in our graph. So in this case, the limit is going to actually be the y value for that hole. So there is a right-handed limit. And then condition 3 says that the left-hand limit and the right-handed limit have to be equal. So in this case, we're going to ask ourselves, the y value for a left-handed limit, is it the same as the y value for a right-handed limit? In this case, no, they're not. So is this continuous? So another example of a limit that wouldn't exist, let's say if we have, let's say, a function that we've restricted the domain a little bit. So let's say this is our function f of x, and we're starting at this point a, and to the left of it there's nothing. So in this case, the left-hand limit would not exist, but the right-hand limit does. So in this case, we already know that this limit cannot exist because condition 1 is not satisfied, and because there's no left-handed limit, there can't be a left-hand and right-hand limit that are equal. So condition 3 is also not satisfied. So hopefully that gives you some ideas. So basically the big idea behind this is that those 3 criteria have to be true for this specific point for it to have a limit at this point. If they aren't all 3 true, then there is no limit here. Let's talk about another concept that's connected, which is called continuity, or asking ourselves if a function is continuous at a specific point, at number x equals a. Now, for a function to be continuous at a specific point, there has to be 3 conditions for that point. Number 1, f of a has to be defined. There has to be a specific point for that x value. Number 2, we have to have a limit for that specific x value. And number 3, the function and the limit have to be the same value. So to give you an example here, this would be a continuous function. So at this point, this is f of a. So f of a is defined. And then, if we're looking at the limit, we're looking at from the left and from the right. And they're approaching the same point, so condition 2 is satisfied. And lastly, for condition 3, we're asking ourselves, our f of a value, is it the same as our limit? So basically we're looking at the y value for each one of these, and they're the same thing. So yes, it is continuous. Let's take a look at a couple of other examples just to give us a bit of a broader understanding here. Let's take that piecewise function. So we said this is this one, we're going to have an f of a value, which is our point, but we don't have a limit here. So condition 1 is satisfied, but we already said this one does not have a limit, so this is not going to work for us. So we can't; those two can't be equal, so those are not continuous. And one more point, and one more example to help us out here. Let's take that parabola, but instead of having this continuous point here, let's make a gap here and let's move that point down here. So in this case, f of a is defined. The limit's defined. Looking at the left and the right, we approach this hole here. But thirdly, are those two things equal? Are their y values the same? So in this case, that one's not satisfied, so this one is discontinuous at this point. So basically, that's the test to tell if a function is continuous at a specific point. But we can also talk a little bit generally and talk about if the function is continuous in general. So if we talk about a function being continuous, it has to be continuous at every single x value. So for all x values that are in the real number sets, if it works for every single one, then it is continuous. So basically, if it has holes or gaps, it is discontinuous. So that's your big quick introduction to limits and continuity. Now that we've done that, let's talk about some specific functions and some other big ideas here. So the next thing we're going to talk about is what we call end behavior. So basically, when we see end behavior, we're talking about at the very ends of our function. So when we talk about what happens when x approaches infinity or x approaches negative infinity. So in example 1, we can already see that this is a sequence. It's discrete data. It's hard to tell if it's continuous or not, but in this case, we know that there is a pattern here. So we're going to just draw a line through it just to help us out. Essentially, this graph here is modeling the sequence a third, 1, 3, 9, 27, and so on and so forth, to 3 to the power of n minus 2. And we're basically trying to examine what's happening as n approaches infinity. So it's first asking us to state the limit if it exists, or explain why it doesn't exist. So we're just going to quickly describe what's going on here. So in this case, take a look at our graph. We can see it's increasing, and there's pretty much as x approaches, as we get higher and higher n values, our t of n value is going to get higher and higher as well. So in this case, there's nothing stopping it. So we're going to describe it as increasing without bound. It's just going to keep getting higher and higher and higher. And it's never going to stop. So for part 2, it's saying write a limit expression to represent the end behavior of the sequence. The way we're going to write that, the limit as n approaches infinity is equal to positive infinity. Let's quickly break that down a little bit just to make sure we understand this. So in this case, the limit as n approaches infinity, of t of n, that's a very important part. So Basically, we're talking about as n gets closer and closer to infinity, as n increases higher and higher and higher, and we're looking at the function t of n. And basically, this is telling us what's happening here. Now, in this case, this kind of probably goes against the logic a little bit that we've set up so far, but when we talk about end behavior, we know that we can't really look on the other side of infinity. We can't look at the right side of positive infinity, but we kind of know that that's where we're headed. So with end behavior, it doesn't exactly follow those rules. When we talk about left-hand and right-hand limits having to be the same, it's more for defined values for a function. When we talk about end behavior for positive and negative infinity, it's okay because we know that it's going to keep increasing. So we know that's the value that we're approaching. So in this case, this works. So what this means is the value of our function as n gets closer and closer to infinity for our function t of n is it's going to be positive infinity. So now that we have that, let's take a look at another sequence and see what we can do with this. And of course, my notes here are a little bit not really well spaced out. I'm not sure why, but let's go with it anyways. So in this example B, we have a half, 2/3, 3/4, 4/5, 5/6, and so on and so forth, all in the form n over n plus 1. So the denominator is always one more than the numerator. So again, let's start by analyzing what's going on as we get closer and closer to infinity, because this one is not as easy to define. So we can probably see what's going on here a little bit according to our graph here. But we're not sure exactly. We want to be a little more mathematical about it. So let's start by, we're just going to take a big number and test our theory a little bit. So let's do t of 100. So that's going to be n over n plus 1. So in this case, our n is 100, so it's going to be 100 over 101. And if you punch that into the calculator, you're going to get something like 0.9900099. So we're getting pretty close to 1. But let's see what happens if we pick a bigger number. Let's pick 1,000 this time. So that's going to be 1,000 over 1,001. And that's going to be 0.999008 or something like that. So we're getting a little bit closer to 1 still. Let's pick one more. Let's do 1,000,000 this time. That's going to be 1,000,000 over 1,000,001. That's going to be 0.999999. So in fact, as we get bigger and bigger, we get closer and closer to 1. So if we were to describe this limit here, that's going to be the limit as n approaches infinity. As we keep going towards the right of our graph, this function, t of n, is going to be equal to 1. So the limit as n approaches infinity of t of n equals 1. And in fact, you've already seen this before, but you didn't know what it was. This is just the basic definition for an asymptote. So here's 1 here. Basically, we're just going to keep getting closer and closer to that number 1 as our n gets closer to infinity. So essentially, we've just used limits to define an asymptote, except we just didn't know what limits were at the time. Let's do one more problem just to give us a bit more information here. Now, we have this function f of x equals x cubed minus 4x. And what we're going to do is we're going to look at this point, x equals 2. So So let's see, it's a little hard to read here, but this is going to be this point here. So the first thing it's asking us is, this is the limit as x approaches 2 from the right. And again, we have this little plus sign just next to our 2, which means the right-handed limit instead of a positive 2. If the plus sign is before the 2, then it's a positive 2. We're just talking about the general limit. If it's on this side, it means that we're talking about the right-handed limit. So in this case, we're looking at what's going on from the right side. So in this case, we're approaching it from the right side, and we see that our y it's going right towards the x-axis. So we're just going to state the y value that we approach here. So in this case, it's going to be 0. Part B asks us for the left-hand limit. So we're going to look at what's going on from the left side this time. And again, it approaches the same y value. It's going to be 0. And next one, we're going to look at general limits. The limit as x approaches 2, and we know it's general because there's no plus sign, no negative sign. So basically, this is asking us, do we have a left-handed and right-handed limits, and are they the same number? In this case, yes, they are. Because they're both 0, means the limit is also going to be 0. And lastly, f of 2, because there's no holes or gaps, we know it's also going to be 0. So last thing we're going to state here, the function has a limit for x equals 0 and is continuous. The function has a limit for x equals 0 and is continuous. So, like I said, this is a slightly different way of looking at things, and for some of it, it might seem a little bit like stating the obvious, but as we talk more about calculus, this concept is going to be more and more important. So just hang in there, and hopefully things will make a bit more sense as we go. So, thank you, and I'll see you with 4.4 next. Take care.